Good morning, everyone. I'm going to be talking about 3D printing, metal 3D printing in construction, focusing on the MX3D bridge in Amsterdam. So I'll say a few words about, generally what this bridge is looking like, and then what we've been doing for the past few years to try and assure its safety. So we've been looking at testing the material of this bridge, testing bits of it to destruction, testing the full bridge, and I'll also be talking about some sort of future opportunities, potential opportunities for this technology. So this is what the bridge looks like. It's been 3D printed by a company called MX3D, based in the Netherlands, designed by Arup, and tested and analysed by me and my team at Imperial College. The bridge and its parts were tested within the construction period and after the construction had finished. And it's now fully open to the public across a canal in Amsterdam. It's 10.5 meters in span, about 2.5 meters wide. It's 4.6 tons of printed stainless steel, and that's all of the structural elements of the bridge. And then there's about 3 tons of deck plate and finishes and end beams in conventional stainless steel. There was about 12 weeks of printing, and that was spread over a 6-month period. And the handrails of the bridge are 3.5 millimeters thick, and the substructure is 8 millimeters thick. So the technology used to build it is called wire and arc additive manufacturing, or WAM. Its technology is based on a robotic arm holding a welding torch. The welding torch is then guided to print the structure, build it up layer by layer, but using technology that we're actually pretty familiar with. The welding technology is the same as you'd use for normal welding. The consumables are welding wire. Again, that's familiar for steel fabricators. So here's a video sort of showing part of the bridge being built up layer by layer. This is obviously speeded up, but you can see how the bridge is growing along its length. It was built in 2.5 meter segments, and these segments were then manually welded together. So what have we done? We've been testing the material of it. So we've taken some plates, we've cut out some coupons, and we've looked at their stress-strain characteristics. We thought there might well be a directionality to the properties, so we tested material in different directions relative to the print layer direction. We also thought that the surface undulations might have an effect on the performance, so we milled down the surface to make it smooth, and so we could compare the behavior of the machined material and then look at the influence of the surface undulations as well. And these are some typical measured stress-strain characteristics. And what you can see is that there's a bit of directionality to the material, so the properties are a bit different in different directions. That's called anisotropy. But overall, we've got good strength, stiffness, and ductility. So that was for the machined material. We then looked at what's the influence of this as-built undulating geometry, and we found that it causes about a 5 to 15% reduction in the key mechanical properties. But ductility was a bit more sensitive. So the effect of the undulations was to cause local low points in cross-sectional area. The deformation tended to home in to those areas, and that caused a reduction in ductility. And you can see that on some coupons where we've got a before and after picture. So this is where the loading is along the weld layer direction, and this is the most ductile. And then at 45 degrees, and then at 90 degrees, when you're pulling across the weld layer direction, you get lower ductility. So that was the material. We then looked at some components, and the idea here is we got components printed which represented parts of the bridge. And we tested these to destruction and compared their response to traditionally produced material. Because of the undulating geometry, it wasn't quite so easy to simply measure thicknesses and dimensions and so on. So we used 3D laser scanning in order to capture a full sort of digital image of the sections. They're tubes, and so it's not so easy to scan the inside of tubes. So we decided to do some silicon castings. So we filled up the tubes with silicon, it set. We then pulled out the inserts, which was not quite as easy as we hoped it would be, but they came out eventually in one piece. We could then scan the inside mold, and we could join the inner and outer scans and get a full representation of the sections. This was really useful because it gave us information about the geometric variability associated with the process, and of course that's important for assessing the safety. We then tested some of these sections under pure compression, and we got this sort of local buckling failure mode that you can see on the right. And we compared the results with what you see or what you're given in current design codes. And what we found is, provided you normalize your results by the as-built material properties, so the ones where you've got the effect of the geometric undulations, that's shown by the red points here, actually, you're getting points that are safe-sided relative to current design guidance. So actually, broadly speaking, they follow the anticipated trends that we're used to. Similar, so that was looking at cross-sections and short columns. We also looked at longer columns. We tested them with pin-ended conditions, so we're looking at their buckling behavior. And this is an example of where we used digital image correlation to track the deformations of the specimens, and you can see how it failed. So this is a combination of overall buckling and local buckling of the columns. And again, if you compare to current design guidance, provided you use the properties of the as-built material with the effect of the geometric undulations, broadly speaking, current design curves quite well predict the behavior of these sections. So this was comforting. All of that testing was to destruction, and then the final set of testing was on the bridge itself, and we didn't want this to be to destruction, but we did want to go up to the design loads that the bridge would be subjected to in practice. So we had 4 trips over to the Netherlands. First trip was in November 2017, when the first 2.5 meter length of the bridge had been built, and we did some preliminary tests. We then went back when the full bridge had been printed, but with no deck in place. And then in 2018, the deck was welded in place, and we did what we called the serviceability loading tests. So this was up to the serviceability design load of the bridge. And then the final set of tests, we went up to the ultimate limit state design load of the bridge. And with all of these tests, we were recording lots of information about how the bridge was behaving and comparing with some models and so on that we'd made. 2 main loading arrangements. So one was horizontal loading. We were pushing out on the handrails and pulling in on the handrails, simulating sort of crowds on the bridge. And then we had vertical loading. Initially, we put water tanks on the bridge, 1 meter cubed, filled them up with water, and that applied a total of 4 tons of loading. We got the England flag there. These tests were done during the World Cup in 2018. We were in the Netherlands. They hadn't qualified. We thought we'd just make our point. We did quite well. And the bridge deflected about 14 millimeters and under this 4 tons of loading, and that was similar to our finite element model predictions, so that gave us a bit of confidence in the model. And then once the deck had been put in place, we went up to 10 tons of loading, and you can see on this photo, it's a combination of concrete blocks and water tanks. The bridge had a slightly stiffer response with the deck in place, so the deck was helping, and it deflected about 25 millimeters under 10 tons of loading. Once we'd done the serviceability tests, that was then enabled us to open the bridge to the public on a sort of temporary basis, and it was opened in October 2018 at something called Dutch Design Week, and people could come and look at it, and it was actually nice to see people, touching it, asking questions about it, how on earth has this been made, and that kind of thing. One particular group got quite excited, started jumping up and down.
Again, did you guys?
And they caused a slightly disturbing sound, which you'll hear in a second,
Okay.
on their second jump.
Jump!
That was a bit concerning at the time. A few people were looking at each other. Someone had dropped their bag on the bridge, and so it was nothing too sinister. So the final set of tests were in September 2019, and the idea here is we were going up to the full ultimate limit state design load of the bridge and a bit beyond. And this was a requirement by the local authority in order to get approval for the bridge to be placed and open to the public. So this time the bridge was loaded with a combination of these concrete sort of tiles. So there's 2.5 tons per layer, and there were 6 layers of these concrete slabs. They were put on one by one with about 6 people, and we put them on in a sort of pattern such that we kept roughly uniformly distributed load over the structure. We then used the water tanks to go up to the ultimate limit state design load. We didn't want to be on the bridge whilst we were putting on loads that we hadn't been up to before. And we got some local students to jump up and down a bit on it as well. And these were at loads quite considerably below what we'd been to with the slabs. Exciting music. So this is the bridge testing team. We were particularly happy that it didn't break, so we had a bit of a celebration. And, we were in the unknown territory here. There was a possibility that the bridge might not have been able to achieve the applied loading. Our models suggested it would, but there was uncertainty. So we were pleased when it survived, and it performed as we hoped it would. So I said we had finite element modeling going on alongside the physical testing. We used the material properties that we measured as input, and we were kind of checking the model against the bridge performance at various stages. And we could also use the model to look at other load combinations, and we could identify, which one would be the critical one. So about 4 months ago, the bridge was opened to the public, and it's now been fully open and fully operational for that period. And we are monitoring the bridge. So there's various sensors that are sitting on it and telling us what it's doing, and we're looking out for, if there's any change in behavior and so on. Okay, so what else might we be able to do with this technology? Well, I think 3D printing is likely to complement rather than replace conventional production processes. I think there will certainly be a demand for more landmark, one-off kind of special structures. But I think there's potential for much wider use in things like structural details. So printing connections, stiffeners, the kind of things that steel fabricators are very familiar with, and towards more automated fabrication. And I think there's also opportunities for strengthening and repairing existing structures. And this is really the direction that the research is heading in. So we've done, for example, some tests on lap shear connections and T-stub connections. These are the building blocks of all sort of structural steel joints. And we found some nice ductile behavior, so that's very promising. And of course, with 3D printing, you can have more fancy geometries, so you should be able to have more optimized structures where the stresses are kind of flowing through the connection in a more efficient manner. And generally, you can have more optimization of structures. Previously, you can create an optimized geometry, but it's not necessarily practical to fabricate. 3D printing does enable you to print a wider range of geometries at relatively little added expense. So in this case, we've optimized some trusses, we've done some finite element modeling, they've been printed, and the next step is that they will be tested. And I think overall, the ability of 3D printing to put material in the optimum location to resist the applied load, to tailor your material properties to meet the particular stress and ductility demands. For example, high-strength steel has lower ductility than normal strength steel, and that can lead to problems in things like connections. If you have the ability to mix your material, you can use higher strength in locations where you need it, but ductility demands are lower, and lower strength in things like the connections and so on, where you need that ductility. So I think the ability to do this kind of thing brings clear potential opportunities for reducing material use and waste, as well as increasing automation in construction. There are, of course, challenges. The cost. So WAM is a relatively low-cost method of additive manufacturing. There's many different methods of additive manufacturing. WAM, I think, is the one that is most suitable for the construction industry, for the scale and cost and so on. Process and product variability. So we've got well-established standards, quality control processes, statistics, etc. for normal steel. We don't have this for 3D printed material. And you need to know this kind of information in order to decide safety factors and so on. Geometric freedom is good in a sense, but you've got to design it. And if you open up Eurocode 3, you're not going to find anything that is going to be suitable for this kind of thing. So we need to think about how we're actually going to design these structures, and it's probably going to mean more sophisticated analysis and design techniques, finite element modeling, this kind of thing. And ultimately, the challenge is, of course, to make absolutely sure we're not compromising on the safety of the structures, and that's the sort of overarching demand. So a few conclusions. So the use of metal 3D printing is growing across many different sectors. For construction, the WAM process is the most suitable, I think, and is showing some promising results. The MX3D bridge it's a one-off, but it's great because it shows what can be done. It gives us insight into what might be possible in the future. I think there'll be opportunities for wider use of this technology in things like strengthening, connections, stiffeners, increased automation, reduced material use in our sector. But of course, there's a lot of challenges to overcome, and as a researcher, that's what kind of makes it exciting, and that's what we're working on at the moment. And with that, I'd like to finish. Thank you very much.